Welcome, everyone. Welcome, everyone. My name is Isra Ismail. I'm a senior civil engineer working at Enel, so mainly on infrastructure projects in North America. I have worked for more than 10 years on civil design using a variety of Autodesk programs. I've been involved in large-scale renewable energy projects. Our goal currently is to continue developing innovative solutions to automate the design process of project infrastructures and optimize design in terms of time and cost. Next, please. So just to give you some overview on the company that I'm working in and the project that we are doing, we are working on a large-scale renewable energy project, including wind, solar, hydrogen, and sometimes geothermal. Basically, we are operating in more than 30 countries around the world, and our goal is to continue working on sustainable sources of renewable energy. Next, please. So in this presentation, basically, we are going to work and review two options, which is and present two options, which is the traditional method of design and the using automation approach. So in the design phase of infrastructure projects, automation approach design can offer tremendous benefits to engineers. Basically, as I mentioned earlier, we work on larger scale projects. Sometimes road design checks in this kind of large size project, kind of hard task to do. Like it's a tedious process, and sometimes you need to work with more than 50 acres of land and design all those roads and crane pads and all infrastructure associated with these projects. So Dynamo for Civil 3D can enable the importing of multiple land XML files, not necessarily developed in Civil 3D. So the designer or supplier that we deal with them, not necessarily using the Civil 3D. So we trying to find a way, since they provide the drawings in land XML files, we're trying to find a way to use the method of automation in order to meet our requirements. So instead of using Civil 3D design criteria with limited number of design parameters, Dynamo can increase flexibility. We can check more parameters and create automatic reports. This design check compromises the first step of a complete innovation path, eventually leading to a more comprehensive automation. Next slide, please. So the objectives and contents of this presentation, we are going to present first the objectives, what the objective of this presentation, and then I'm going to go over the typical process when using Civil 3D. And then my colleagues, they are going to talk about developing the new process by automation. And then also they will discuss analysis of the benefits of this approach. And finally, what is possible future improvements that could work with this. Next. So as I mentioned earlier, I'm going to discuss the typical road design process using Autodesk Civil 3D tools, including importing land XML file, setting design criteria, checking road parameters, including horizontal and vertical elements, fix any design requirements violation. And my colleague, they are going to present the new approach of road design checking process through automation using Dynamo Civil 3D. So basically, they are going to discuss the new workflow and the input database to start the process, and then checking horizontal alignments and vertical profiles, and then create design reports. And then at the end, how we tabulate those results and import it to Excel file. Next, please. So the review of the typical process. So basically, in the traditional methods of using Civil 3D, we receive all land XML files, including let's say surface, profiles, alignments in land XML file. And so we import it to a Civil 3D. And the next step, the next slide, please. The next step is we work on those surfaces. After we import it, we work on the styles if we need to develop anything. And then after we set all the surfaces required for the project, we started designing or having the alignment and the profiles. Actually, before doing that, we set the design criteria. So as I mentioned, for example, in wind project associated with a kind of special delivery requirements, because we deal with wind turbines, which sometimes it goes to up to, let's say, 180 meters. So the delivery vehicles of this, they have like specific requirements. For example, the turning radius, the K value, all of these parameters need to have a specific requirement. And this requirement, actually, supplier always has their own requirements because they are going to deliver those turbines to the site. So at the beginning, we take the information from the supplier. We set the design criteria, including, like, let's say, the slopes, the K value, the radius, the turning radius, the curve length, etc. So there are the one that who work with Civil 3D knows that there are two ways of setting the design criteria, either with design criteria editor or with design check tools. Next, please. All right, so basically, as you can see here, once we set up the surface that we need to build on, we create the horizontal alignment. And horizontal alignments, of course, need to meet the requirement, let's say, for the radius, for the curve length, for the tangent. All of these parameters need to be aligned with the design criteria. Next. The same for vertical profiles. The vertical profiles, as you can see here on the profile, the most important elements are the K value. We need to make sure that the turbine vehicles, let's say the one that hold the blades, does not. We need to make sure that the blades does not hit the ground. So therefore, they need to have like specific clearance. They need to have specific K value. So this needs to be checked through the design. Using this is the traditional method. Next. So finally, once we have all of the design, let's say the alignments, the profiles, and all of the objects for the roads or the turbine pads, we check if there's any violations because we already set the design criteria. We check if there is any violation for the radius. We need to have specific radius. We need to have specific slopes. Like, let's say, in turbine vehicles, we have maximum slopes. Usually, we don't take more than 8%. If it's above 8%, then we need to get back to the supplier to discuss that with them. But basically, any violations need to be addressed. And next slide, please. So all the violations, all the warnings, as you see, there's yellow warning. We go to the geometry. We modify the geometry. And we modify if we need to have like larger radius, we need to have larger curve length, or we need to fix any. We need to have, like, for example, recently we were dealing with a huge turbine blades, which is need like key value to be more than 28. So we always make sure that for this specific requirement, we need to have K value more than 28. Under that, if the K value less than that, we need to fix it. We need to do some improvement for the road. Next, please. So basically, these are the traditional way and the typical way that we usually do in our project for like checking and designing the roads. As I mentioned, there sometimes we work with more than 50,000 acres, and that's a lot of area and a lot of roads and a lot of paths that need to be graded. So just working on this repetitive task is kind of time consuming, and it takes time and cost as well. So that's why we need to improve here. At the same time, basically, when we do the design, sometimes we need to have report or history of modification that because the design keeps changing from day one until the end. So that's why we need to have history of modifications made over time. And finally, when you do a huge number and a lot of design and a lot of you deal with a lot of parameters, you have a high possibility of human errors. And in this case, that's why we need to shift to something more efficient, which is automation process. Next, please. So what we need to improve, we need to improve the workflow with automatic process using Dynamo. And then we need to reduce the errors. We need to reduce the time consumed for this task. And finally, we need always to have data and history information. So whenever there are we need to see what are the changes over the life cycle of the project. We need to have all of this information. That's why we need to shift to automation procedure. And I guess that's it. Now I'm gonna pass it to Cristiano, I guess.
Thank you, Isra. Hi, everyone. My name is Cristiano Saad. I'm a civil engineer and BIM coordinator at Enel. My daily work involves optimizing processes that use high technology and improve collaboration between people. Just for you, I'm not Mr. Bean, but I love this kind of methodology and I'm passionate about BIM. Now, I will present the proposed workflow. So after the explanation from Isra, I will present the proposal workflow that we understood, which has two crucial points different from the traditional one. It's better structure. It's with study of process and sub-processes. Also, this new process, this new workflow is standardized, and there is a minimization of human mistakes. So in this workflow, we will go through 5 main steps that are preparation of the input database, development of BIM model in CV3D, semi-automatic design check using BIM model. So here it's important to note that it's not totally automatic, it's a semi-automatic. Also, we are creating reports and finally exporting all these results. So the big difference between the traditional and the new one is this process structure and still to be optimized mainly in terms of time, okay, and quality for sure. What do we need to use to develop and to carry out this workflow? We need to use for sure CV3D in 2020 version or 2021, not 2019. Also, we need Dynamo Player, Dynamo Studio with extra package of CV3D toolkit developed by Paulo Serra. Also, we are using some Simply nodes, some Python nodes, and basically this is everything that you need to carry out the proposal workflow. Related to the Python script, we are using base key scripts, so even if the user does not have some advanced knowledge about Python, she or he will be able to run and to understand what's going on in the workflow. So in the first step of the workflow, the input database, we are basically talking about three topics: the drawing settings, the topographic surface, and the LinuxML models. And the drawing settings is related to system units, coordinating system zone, and drawing styles. The topographic surface, we are creating a database that contains digital elevation model or the points x, y, and zeta. And finally, the LinuxML models is the third part of the input database, and it's related to alignments, profiles, and cross-section. We are using version 1.2, but it works also for the version 1.0. We did not test yet with version 2.0, okay? So this is our input database, and now I will explain how we create automatically this input database using Dynamo. So for the drawing settings, the user in Dynamo Player needs to configure three things. So the system code, system units, and drawing styles. These three inputs here by the user can be done by the Dynamo Player, and after the user inserted this information, it's necessary only to play a button. Inside this Dynamo script, we have some simply nodes, some CV3D toolkit nodes, and also some Python nodes. Here you can see that our Python nodes basically execute some CV3D APIs related to commands, okay, and to settings related to the drawing. So are very basic, okay, we are not talking about advanced programming language. Also, as lesson learned from this script, we observed that it was necessary to create a random polyline and alignment during the process in order to create the drawing styles. These temporary objects are created at the beginning of the script, and at the final of the script, these objects are deleted, removed from the model, but the styles remain in the model database. So there are alternative solution for sure, but this was the one that served us more satisfactory in relation to the complexity of the nodes. So using this kind of procedure, we just use simply nodes to create the styles, okay? So here you can see very fast the procedure. It took less than 1 minute to configure everything. For sure, you can do it manually, but as we mentioned before, we are trying to avoid human errors, so we simplify the inputs to avoid mistakes. And as you can see, after running, it looks really fast, the configuration. So if you check the drawing settings, you will see that everything was configured, okay? The second script, so the second script is related to the topographic surface. Here we have the most challenging situation. We know that this procedure is relatively simple in the CV3D tool, but we find it interesting to insert it as a script to avoid the user forgetting to put it in the model. We also know that this processing typically takes time when terrain elevation models are heavy. However, we do suggest pre-processing the surface with InfraWorks or similar software to convert the digital elevation model format into IMX format file. Using the IMX, the user will save time in processing within CV3D. So here we know that the process of create the surface takes a long time normally. So we suggest the user to convert first to IMX using InfraWorks, for instance, and then with the IMX, put it inside CV3D. Thus, as shown, the user can use or IMX or the points. So also the user can select the points For the IMX, we are using send string to execute, also a CV3D API inserted in a Python node. And for the XYZ, we are creating Cogo points and then the surface. So basically, some nodes from CV3D Toolkit and from CV3D, Dynamo for CV3D. Okay. The process is quite different between the two. So as you see here, the process is a little different, but the time is more different. So using IMX, the pre-process surface, we are taking about 5 minutes in a surface that has about 5 giga of size. Using the XYZ, we are spending 10 times considering extensive topographic surface. For obvious reasons, we will not show the surface processing video. It's here, but it took a long time to see the results. Then, related to the third part, the third key input to create the database and develop the CV3D model is related to the road models, so the LearnXML. This is an open format. We understood LearnXML as an open bin format. It's like a specific format, very old for infrastructure design, okay? And we tried in the beginning to use IFC, but it was not very good inside CV3D. So the solution was using LearnXML. And here we are using LearnXML because some designers are not working with CV3D. So they can then send us another format to be ready. So this one is the format that we choose as a collaboration format between designer and our team. Understanding this as an open flow implementation, we are using this format that can be exported from the main access design tools. Obviously, if the designer directly sends the CV3D model, the user can skip this step as the CV3D model will be practically ready for checking. In the simulation that we carry out, the LearnXML basically contains 3 sets of information in relation to alignment. So we have the coordinate geometry, basically the horizontal alignment, the profile, the vertical profile, and the corridor section, so the cross sections, okay? It's not the assembly, so it's different from assembly. And for the process of these LearnXML files, we again use basic Python nodes in which API methods were used within the LearnXML in common. A difference of this routine in relation to the native functionality of CV3D is that we create a loop sequence to import several files at once, not one by one. So we can import multiple LearnXML one by one, which is not possible by the native method in CV3D. The processing time to import it, so to import 4 large models, it took 1 minute. So it was really fast. As you can see here, we have the surface here in the background, some design lines, not the models. We selected the folder containing all the LearnXML, okay? And after running, it took some seconds, really fast, and we have all the alignments, vertical profiles, and cross sections inside the CV3D, okay? The cross section actually we cannot see, but we are developing other scripts to see it. Now, related to the next steps of this new process, I will give the floor to my colleague, Eliza.
Thank you, Cristiano. I'm Elisa Ambrassa. I'm a BIM coordinator for Enel Rome office. I have over 3 years of experience in the civil engineering industry, and I'm a licensed structural engineer. The last 2 years have been devoted to automating the design of wind and solar plants with Revit and Civil 3D. And currently my focus also lies on coordinating multiple disciplines as being coordinator in projects all over the world. Please, Cristiano, you can go on. Our goal is to check the parameters such as the radius of each alignment and the vertical profile slope, as Isra mentioned before, for which we have specific requirements in our technical standards. These present an alternative to the design criteria that can perform geometric design checks only for limited design parameters. We know that we are in the beginning of this process and we are checking only a few parameters, but we understand that Dynamo gives us a big flexibility and we can evaluate more parameters also in the future. Please go on. So starting with the first script that checks the plan radii on the alignment, the inputs that we can see here are the minimum radius required and the directory path where we can save the report. When we run the script, please go on, we can see appearing a pop-up, and that informs the user that the property set have been created. To do that in Dynamo, we can link a JSON file with the custom properties, as we can see here to the left. After that, the script checks the radius in the middle of each arch of the alignment, and it compares it with the minimum value required, as we saw before in the inputs of the Dynamo player. From this analysis, it creates and places the alert, taking the form of 3D spheres in a similar way that is using Civil 3D, that is placing yellow warnings. So here we can see here these spheres, the red and the green ones. So we created for that 2 different layers that are assigned to the spheres, which will appear as green if they pass the check. So if the radius is larger than the minimum required, or red if the radius checked failed. Afterwards, the property set and the values are attributed to each alert. In particular, we can see here in this table, we define the check-in date, the design radius, so the radius that is designed by the project team, a UID that is an issue identifier that we decided to compose it by the object handle of the object itself and the start and end station. The last 2 properties are the layer that identifies if the object passed or failed and the minimum required radius as is defined in our standards. The first example here that we can see is for the radii that passed the check, so are highlighted here in green. And the second example is for the red, so for the ones that failed the check. Once Dynamo player finished the analysis, as output we can have here the path where the Excel report is saved. The report is customized and contains for each alignment the station in which the radius failed or passed the control, with in the last column the design value. Because of the overwriting, the report will append for each run a new sheet that contains the check data. This enables us to track the history during the entire life cycles of the project. The same for the profile check. So let's pass to the second script now. And this is the check of the maximum vertical slope that we can have on the alignment. In a similar way that we saw before, the inputs are the maximum slope and the directory path where the Excel report will be saved. By running it, as for the radii, a pop-up appears and it informs the user that the property set have been created. To do that, in Dynamo, we link the JSON file with the custom properties here to the left. After that, Dynamo creates the profile views for each alignment and places them one under the other. So we can see here that from the polycurves that are created as connection between the profile vertical intersection, so I mean the PVIs of the alignment profiles, we can get the curves. So we can see here the Dynamo script that it's appearing, it's appearing now. And then after that, we can calculate the slope that it's in the middle point of each curve. Afterwards, we can have this visual alert. And so we have these rectangles that highlight the area in which the vertical profile values either complies with the predefined standards or not. And that are created in places on the profile views. Logically, again, the green ones are the one that complies and the red one are the one that failed. Hereafter, we can see the property set and the values that we attributed to each alert as before. So we define in a similar way to the first code, the check-in date, the design slope. So again, the slope that is designed by the project team. The issue identifier, again, composed by the object handle and the start and end station. And then the last properties are the layer that identifies if the object passed or failed the check, and then the maximum slope required as in our standards. Then we have this first example that shows the area in which the slope passed the check, again here in green. And then the second example that we can see after for the failed ones in red here, okay. With the same logic of before, the path where the Excel report is saved is shown as output of the Dynamo player. The custom report contains for each alignment the stations in which the vertical slope failed or passed the control, with the design value at the last column. Again, because of the overwriting, the report will append after each run a new sheet containing the check data, and thus we can track the history of these values during the entire life cycle of the project. So now I give the floor to Marta that can proceed.
Thank you, Lisa. Hi, I'm Marta Bandino. I'm a licensed construction engineer working in Enel. I have 3 years of experience in working with Revit and Dynamo, especially for the discipline of architecture, map, and building. And now in Enel, I collaborate for the BIM implementation with automation for wind and plant design and model checking. So we can go on. After all this step of importing the model and checking the project, we would like to create a single file where we can both have a summary table of the check and the graphical part of the checking results, so the sphere in green or red, or the path in green or red for the profiles. This will serve both as a file to be stored in the project report history, but also to be used by all those people like civil infrastructure expertise who are not user Civil 3D and who will not be able to easily navigate the model in order to analyze and check all the errors and possible improvement. The best way that we identify is the export of PDF file. And so we have to insert the Excel report, so the table, in the graphical part of Excel, of Civil 3D. So Cristiano, can we go on? So for this first part of insert the check-in table in Civil 3D, we use another Dynamo script, and it concerning to customize, select all the information, the properties that we want to insert in the table, so with the column. And so they can select like the grid, the check-in date, the with date of the cell table, or the fail, or the good one result, and so on. So like the other, go on, Cristiano. This Dynamo is a simple Dynamo where we use some Python node and some simple node. In the first part, we select all the elements inserted in Civil 3D, and then we get all the property set that we set previously with the other script. And then we list this element with the title of the table and create the table with a simple node of the Civil 3D Dynamo. And so if we go on, we can see the processing Dynamo player. So here you select with the true and false with the Boolean task the true or false for what properties that you want to see in the table, and then you can select run. And in the Civil 3D, you can find the two tables: the one for the check-in radius, and the second with the check-in vertical profile. Is the same information that we see in the Excel exportation, but we see it directly on Civil 3D. The second point that we want to create is a plot PDF. So we want to print this PDF in our PC so everyone can see out of the box Civil 3D. This is a very simple script where you have to choose false for the manual configuration, the automatic configuration of the print plot of the print, and if you want to go on with a manual setting of the print, you have to set true. So go on, Cristiano. As you can see, there is very simple Dynamo graph. We have only 4 nodes. 2 are some Python script, and the other is an if node and a true or false. In the first script, go on, Cristiano. The first script, Python script, was for the manual export of PDF. So if you select true, go on the Dynamo go on only with this node. It is a simple 2-line, very simple 2 or 3 line of script with where we call a command on the line that was _print. And go on. If we set true and then run the script, the Civil 3D go on with the window, the generic window of the plot model, where you can set the dimension of the sheet, the scale, and so on, and then click OK, and the Civil 3D prints you the file. In the second Python script is the ones for the automatic print. So it's a few lines of script when we set all the properties that we want to see in our sheet, in our file. So if we go to the Dynamo player and set the false value and click run, we see not the previously windows of the preferences print, but we see directly the plot progress. So Civil 3D said to us that he go automatically on with the print. So we have to wait only the time for the print. So the final result of both the bool selection is a PDF file. It's not so different from the one, and gone. So we see the graphical part with the alignment, the surface, and the profile, and the tables that we want to see, all in one file. So everyone can check, control, and do what they want with these files. So for now, this is what we have managed for the development of this new workflow. But we have already several improvements and next step that came in our mind. Go on, Cristiano. Such a creation of as many controls as need for the development of the project, following the guidelines of the company or the country where the project will be realized. And another next step that we want to implement was an automatic correction of the simple errors. So maybe, for example, if we have a road with a radius of 195, but the minimum required is 200, we can ask to Civil 3D to automatically correct these minimum errors. Another one that we try to implement was the create an automatic zoom on the error. That is something that our colleagues try to ask to us, because it's a simple mode to identify the errors in the table and then also in the graphical part. The last two steps that we want to implement was the cut and fill volume, so the automatic calculation of the cut and fill volumes, and also the add-in of the price list, so we can help us to individuate the economical and ecological cost of the project in order to improve it. So this is only just some of the possibility that LandXML, Civil 3D, and Dynamo give us for the development and analysis of infrastructure project. We hope that, thank you to this class, with your questions and opinions, we will be able to improve everything and develop a more complete and competitive workflow. So thank you for watching, and see you later in the Ask.